Thank you very much, and thank you for the invitation to the MEMO webinar today for quantum optics. And I would like to talk about something a bit different, and I named this talk Unconventional Imaging. So I'm going to start explaining what does it mean by unconventional, and then I'm going to explain why we use entangled photons for it. So let's just imagine like a very normal scenario, right? So you have an aperture or an object that you want to make an image of. What you normally do, for example, here in transmission, you shine some light on it, you put some optics in between, and then you have a camera that has, of course, the spatial resolution. And this is going to give you the image of the object you want to see. However, there are some other imaging schemes, unconventional ones, where the camera is actually not measuring the light that passes through the object, but it is measuring another beam of light, for example, here in another wavelength, for example, a visible. And what's peculiar about this is that this other arm does not interact with the object. We are able to get an image of the object. So it looks very weird, right? And this is what we call the non-local image, because the camera is somewhere else measuring some other beam of light. And even though the setup is like this, we are able to retrieve the image of the object on the other side. And if you can see there, the biggest advantage of this is that we can do either at the same or a different wavelength for these two beams of light. So this means, for example, if you have an object that you cannot illuminate with a very short wavelength, then, for example, you can use a near infrared, but then you run into the problem that a camera in the near infrared is not very efficient. So with this type of unconventional imaging schemes, you can bypass this problem by putting the camera somewhere else and measuring, for example, in the visible, where we know that cameras are very efficient. And well, how does this work? This very weird scheme work? I would like to just present to you the content of my talk today. So I will talk about a bit of the basics that you will need to understand this scheme. And then I will talk about the two famous setups that implement this unconventional imaging. The first one is called imaging with undetected photons, and the second one is ghost imaging. Everything in quantum optics or quantum mechanics always has like a fancy name, and this is not the exception. So remember the basic experiment as to start just this explanation. You have a single photon and you have a double slit in front of it, slit A and slit B. And after that, you have a detector. So from this very simple experiment, what can you expect? The first thing is this, okay, in the detection, I'm going to see just one photon. And the question arises that through which slit did the photon travel? Then we actually don't know. It could be from A or it could be from B, but at the end, I'm measuring one photon on the other side. So since we don't know through which slit did it go, this is called indistinguishability, because we cannot distinguish which way did it take. Going a bit more into the way we represent this, we can write this formally as a quantum state, like behind the double slit. And since we don't know through which slit did it go, this indistinguishability allows us to put everything, like all the possible scenarios, as a superposition. And just to guide you through the notation here, the quantum state is shown here with the letter psi, and each of these scenarios is represented by what is called a ket in what is called Dirac notation. That's not important. So this is a scenario, and this is another scenario on the right. So I can simply say, okay, in one scenario, one photon is going through A, so one photon here, and 0 in the other one. And the other scenario is, okay, 0 in A and 1 in B. Now, going a bit deeper, and my previous speaker also mentioned about spontaneous parametric down conversion, it's a process that allows us to obtain not single photon, but pair of entangled photons. And for this, we use a nonlinear crystal with a second order nonlinearity. So it's a second order process. And what happens here is we shine a photon that we call pump into this. And what happens is this photon splits in two. And normally they are called signal and idler. I didn't put the color just to make it pretty, but actually it looks like this because the photons that are created conserve energy. For example, the pump has this energy here, and it's going to split the energy in idler and signal. And also in the animation that I showed you before, you can see that there is momentum conservation. That means that if the pump photon is going to the right, then the signal and idler will also conserve momentum. What is here important is the correlation that the signal and idler will have. For example, there is an energy correlation because, for example, if I know the pump energy, I measure an idler, I know immediately what was the energy of the signal. And also with momentum conservation, if I know that the pump is going to the right and I measure a signal going like this, then the idler should go in the other direction. So this correlation, it's called a quantum correlation, and it's basically translated in entanglement and comes from this energy and momentum conservation. So this quantum correlation can happen in energy, momentum, and position. And for our particular application here for imaging, we're interested in momentum and position entanglement and, well, correlation in general. So how can we write the quantum state for this signal and idler photons that are created on the other side? I added here a system of reference. Z is going to the right and X is the transverse component. So for example, this nonlinear crystal allows us to get this down conversion process, but it's actually a probabilistic process that has a very, very low probability. And one of the possibilities that can happen is that a pump photon goes through this crystal and actually there is no signal and idler. So basically we have 0 for signal and 0 for idler. But that's one of the possibilities that go into this quantum state. What could be another possibility? As I showed you before, okay, we get these two pairs with a certain momentum that I call here Kx, which is the transverse component of this. So basically it tells me this ket or this scenario here tells me one idler photon is in the mode Kx1, and the other one is going to be, the signal photon is going to be in the mode minus Kx1, remember, because of momentum conservation. But there are also, of course, more possibilities. And remember, in each of the possibilities, we have momentum correlation. So the crystal can also be adequate to create other Kx vectors. But since this is a probabilistic process, we don't know which Kx will the photon pair will have after this happens. So we have, again, indistinguishability, as I mentioned before. So that's why we can write the quantum state of the signal and idler as a superposition, basically as a sum of all these possible scenarios in these kets that I'm showing you here. So another possibility is that, of course, they can also go straight, also conserving momentum, and so on. Okay, there are many K components that could go there. Okay, so that's enough for the basics, and I'm going to try to explain to you the first unconventional imaging scheme, which is called imaging with undetected photons. And please notice there that I underline the undetected photons because it's how can I image something without like detecting the photons, but you will understand how does this work. And for this case, I don't need just one nonlinear crystal, but I need two. And I named them here A and B. And each of them is illuminated by a pump. And as I showed you before, this is going to create a pair of signal and idler that here I just put a straight photon just as a representation. And also for a crystal B, it's going to happen the same. But what happens if we start modifying a bit this scheme that I show you here? Let's put a mirror and some dichroic mirror there and just direct the signal and idler from the first crystal named A signal A and Euler A. So what's going to happen is, well, the second one is also going to create signal and Euler, but the question comes here. The signal or the Euler photon that's going to come in this side will come from the source A or the source B. Well, it's impossible to know because I'm overlapping this to this from A to B. So when I receive a photon pair, I don't know from which crystal did it come from. So this alignment introduces indistinguishability. So again, we can try to write the quantum state of the signal and Euler at the output of this. And as I mentioned before, indistinguishability allows us to put everything as a superposition of different scenarios, right? But now this scenario includes two sources that I named A and B. So one of the possibilities that I told you before, because it's a probabilistic process that has a very low probability, is that none of the crystals create this photon pair. So the first possibility is that everything is zero, no photons. There is another possibility, of course, that one photon pair is created in crystal A, but no photons are created in crystal B. And also the other way around, zero in A, but one photon pair in B. I just wrote here for one particular mode, so, but you know there are many modes. But there's also a last possibilities that the two photon pairs are created, like one photon pair in A and one photon pair in B. However, this last term here, it's well, it scales with this term square, which is very small, like very smaller than 1. So this is normally 0. But we can further change this setup, and just remember here, before I just put signal and Euler through the other one. But if I take this signal out of this and I leave the Euler, it would look like a setup like this. The Euler A still going through this road, but the signal A, I can put here the correct mirror to separate them and then put them back here. So the signal of A and B, I'm putting through a beam splitter, and the Euler here is overlapping the Euler of A, overlapping the Euler of B. So what happens here? In the Euler, I still don't know from which source do I have. So I don't know if it's A or B. And also by doing this overlap here in the beam splitter, if I receive a signal photon here, I don't know from which one it came, either from A or from B. So this change that I did in the setup still maintains the indistinguishability, and therefore we can still write the quantum state as we know. But now let's change it another way. What happens if I block what's coming out of the first source, the Euler A, for example, with an object with zero transmission? What happens there, as you see, if I have an Euler here below, I'm going to be sure that this Euler is going to come from the crystal B, because the crystal A photon is being absorbed here. And well, for the signal, it's a different story, because the signal is still being created there, but it could have come from A or B. So I have indistinguishability in the signal, but not for the Euler. So actually, this Euler, as I mentioned, indistinguishability disappears, and more formally, the quantum state that I showed you before cannot be written as before, because we don't have a full indistinguishability. I don't want to bore you with the math of how this is implemented, but just trust me, you can just write everything in a very nice way and implement what happens when the Euler is distinguishable and the signal is not. And this interplay of distinguishability and indistinguishability is what allows us to do this weird imaging scheme. So let's just put all the things that I told you before together. So now I'm going to put an object that has, in the white part has a transmission equals to 1, and in the black part is 0 transmission. So as I told you, with transmission 1, completely transmissive, the modes are going to overlap the Euler mode, so I have indistinguishable modes. But in the black part, where the transmission is 0, is like blocking the Euler, and I have, again, distinguishable modes. So this interplay between these two is going to be everything for imaging here. And additionally to this, I put a camera just on the signal one. And what happens when we do this is actually we can retrieve the image of this object on the other side, just with this interplay of indistinguishability. And as I mentioned at the beginning, this is a non-local image, because if you see, the idler photons are the only ones interacting with the object, but the signals never touch the object, and still they are able to manage to do this. Well, everything comes from the entanglement from these photons. But the other very curious thing is that I never say about measuring this idler. So we actually don't care. So we can simply take these idlers, pass it through the object, and just throw it in the garbage, because the image is going to appear in the signal on the other side. It's no problem. And that's why it's called imaging with undetected photons. The undetected photons are the idlers that are here. They are allowing us to do this imaging, but on the other side, we get this non-local image of the object. This was, I just put the reference here. This comes from the group of Zeilinger, and the paper was published in 2014. So I urge you to read in all the different literature that comes in it. So as a summary, to get imaging with undetected photons, I need two sources of photon pairs. I need to superimpose the idlers to introduce indistinguishability, and also in the signal arm with this beam splitter. The object will interact only with the idler, whereas the image is going to appear at a camera that detects signal photons that never interact with the object. And as I mentioned, the idlers can remain undetected, that we don't care about them. We already have what we want. So that's the first part of the first setup. And let me go on for the second setup, which is called ghost imaging. Also a very fancy name for these schemes. But for ghost imaging, we just need one crystal. So we have, again, this nonlinear crystal with a chi2 component, and this is going to be pumped with some photons. And as you know now, you can get from this a signal and idler photon that you can just split. And in the signal arm, I'm going to put a camera, which is a resolving detector. And in the idler one, I'm going to put a bucket detector. Why do we call this one a bucket? Because simply like a bucket is just like measuring everything, but you don't know any spatial information of that. It's not spatially resolved. It's just collecting all photons that are coming. So again, this pump photon creates this signal and idler, and we can put an object here in the idler. I just put a cross section here of this psi letter, so it would look like 3 slits. And just forget for a second about the signal photon there. If we have an imaging scheme just with the idler, we won't be able to get an image with this bucket detector, because this bucket detector is just collecting the photons and not letting us know what is the shape of this image. So one possibility is like these photons are created, it passes through this hole here, and the bucket detector, I put here a check, is going to detect the photon, and the signal is also going to detect the photon. But there could be also the possibility that the idler photon is absorbed by this part here, and the signal is, of course, going to be measured. So the bucket detector doesn't measure anything, but this one does. And I can keep sending more and more photons to this. And after sending many pairs, what do you think we're going to get? Actually, nothing. We don't get nothing. As I show you here, we just get like a lot of photons in the signal, and we don't have nothing, no information about the object. So you can ask me here, okay, Andres, so where do I get the information of the object? Where is my image? And actually, to retrieve the image, we have to put some extra hardware into this. And this is what it's called a coincidence circuit. And what does it do? So it takes also the information from the bucket detector. And as I showed you before, if a signal photon arrives to the camera, but there is also a photon through the idler that's hitting the bucket detector, then that is called a coincidence because there are two photons from one source and the other. But if the either got absorbed, like in the second case, and the signal go through, it's not a coincidence because there is just one photon coming from one source. And this is what does it actually. So taking into account these coincidences, then you can retrieve the object on the other side. And so as you see, the signal that never interacted with the object is in the path where I put the camera. And this was published, well, many years ago in 1995. And there are tons of papers about ghost imaging, and there are still many things that we don't know about it. And that's, of course, part of my research as well. And yeah, so the image appears in the coincidence count. And why the name ghost image? So actually, if you say like the cameras or the detectors are eyes, on their own, as I showed you at the beginning, they cannot reveal any information of the object. But the information of the object is hidden when we take this coincidence circuit in between. That's why it's called ghost imaging. So as a summary, for ghost imaging, we need one source of photon pairs. The object is going to interact only with the idler. The bucket detector is going to simply collect the idler photons, no spatial resolution. And the camera is going to detect the signal photons that never interact with the object. And that is where we're going to get our non-local image on the other side. And what's important here, the image is going to appear by taking into account the coincidences. And notice here that this coincidence circuit allows us to improve the signal to noise ratio, the SNR. Because just imagine, we have some photon coming from somewhere, not from this setup, and hitting the camera. If there is no pair of this signal, of this noise that's coming from nowhere, the coincidence circuit is going to rule it out. So in this way, we can improve the SNR. Okay, as a conclusion to this, I would like to compare these two schemes, these unconventional imaging schemes that I explained to you today. And let's see, they have in common that they produce non-local images that could be at same or different wavelengths. So for the imaging with undetected photons, the interacting photon, with the one that interacts with the object, does not need to be measured. On the other hand, ghost imaging, you need to measure this photon with this bucket detector. But we don't need a fancy, well, we need a fancy detector, a single photon detector, but not spatial resolve. So you can use an avalanche photodiode as a camera, as a trigger to the camera to perform the coincidence, for example. And from the coincidence in ghost imaging, you can improve the signal to noise ratio, which is something very good. Whereas in the other setup, you don't have coincidence, so you don't have the improvement in signal to noise ratio. But imaging with undetected photons has on the other hand, the advantage that you don't need more hardware to perform this coincidence. So both have their good sides, and well, we cannot have everything. And this is basically like an overview of the two setups that I showed you. And with that, I would like to thank again for the organizers, and would like to acknowledge here people in my group, Professor Perch, Professor Staude, Dr. Setzma, and Dr. Eilenberger. And I would like to say, join us. We have many open positions, internships, bachelor, master thesis, everything, you name it. Here's the website. And you can also text me. I can also send you the information. And to finish, I would like to thank you all for your attention.
Okay, thank you, Andres, for your talk. We have a question from Naveen asking: has anyone done experiments to get images using ghost images, or are these still only concepts?
Yeah, thank you, Naveen, for your question. Yes, there are many experiments that I wanted to show, but it was going to take longer. There are many experiments, and we also have one experiment on our own. And I mean, the setups, as I show you, the ghost imaging setup is easier, well, let's say easier to implement than the imaging with undetected photons, but our setups that are complicated. For example, the imaging with undetected photons is basically a nonlinear interferometer. So to align it is not trivial, but yes, they are working. So yes.
Okay. And then we have a question from Elena asking, would it be easy to get the sufficient light intensity?
Yes, you can use what I call bulk crystals for this nonlinear process, and well, a paper is going to be soonly published from a group that works with us, that they can actually make videos using this. So you can get a very large photon flux, and you can make videos out of it. Yes.
Okay. Because I was maybe it's a question for me. I was wondering, as we use only photons, pairs of photons, is it fast, or
Well,
is it fast to acquire images, or
well,
we need long exposition
conventional
time?
imaging is always faster, but you can overcome this this lack of, let's say, very large number of photons like in normal imaging by improving your hardware. You can have very sensitive detectors, and also you can do it in parallel with fast post-processing, and you can try to push the limit a bit further. But of course, it doesn't compare to normal imaging in that sense. Yeah.
Okay. Thank you.
You're welcome. Any more questions?
There's a question in the chat from Arturo. Hi, I have a question regarding temporal frequency entanglement for ghost imaging. I don't know.
Did he mean? Okay, and the question is, you can do it temporarily? Probably, yes, you can do it. There is a paper, people do it temporarily. I mentioned here about correlation between momentum, right, all the time. But this correlation, this modes that I talked here are momentum. And my previous speaker talked about everything that was related to frequency. So this can also be translated to time. And there is also some works with ghost imaging, but using temporal or frequency entanglement. Yes. And also, we're about to publish a paper that we don't entanglement in polarization, in momentum, but in polarization. And this has some great advantage when you do have entanglement and not just like classical correlation. But we will publish it in a couple of months, probably. Yes.
Okay. And then we have one last question from Helena. Are there other ways to generate a pair of photons for this setup?
Are there other ways? Yes.
Other ways than the crystal, I think.
Yes. Well, in our group, we don't only work with this setup, we also work on the sources. How do we design the sources? And you can integrate everything in a photonic crystal. You can also use these pairs if you have enough momentum modes for imaging, or I've seen people also use I forget, four-wave mixing as well. You can also use that process. You can, for example, for this imaging with undetected photons, instead of two crystals, you can have one, but you can simply put a mirror that just reflects the pump, so it acts as another crystal. And yeah, there are many different configurations that you can go with it. And it's a field that it's growing, and part of our work is exploring and try to get a bit more of these setups.
Great. Okay, thank you. I don't know if there are any other questions. There's a remark from Arturo telling that he would like to know more about your work. So
yes, so my
maybe,
email is here.
Yeah, you can send him.
Just feel free to send me an email. And I didn't talk about the details of what we do here because, well, it goes a bit too deep and I didn't want to go in that direction. I can send you also our publications and everything.